Where did Paul go? Okay, well, I can introduce Andrew, as we should probably not stay on some kind of schedule with people coming in and out. I'm sure that will happen on a virtual conference. So Andrew Gordon's a research professor at and the director of interactive. Oh, okay, fine. Paul, you want to do it? You got to unmute, Paul. All right, Paul's still having mute problems, so I'll continue. So he's at the
is it okay now?
Yep.
Sorry. Sorry. So I'm super excited to be introducing Andrew. We've known one another for a long time. He's a research associate professor of computer science and the director of the interactive narrative research at the Institute for Creative Technologies at the University of Southern California. His research advances technologies for automatically analyzing and generating narrative interpretations of time series data. A central aim of his research is the large-scale formalization of common sense knowledge and reasoning with these formalizations using logical abduction. He's the author of the 2004 book, Strategy Representation, an Analysis of Planning Knowledge, and the 2017 book, A Formal Theory of Common Sense Psychology, How People Think, with Jerry Hobbs. He received his PhD in 1999 from Northwestern University, and again, super excited to hear what he has to say today. Take it away, Andrew.
Okay, thank you, Paul. It's good to see you. I hope you're doing well. And thanks Shawali and Matt for putting this all together. I really appreciate the innovation that people are showing and trying to pull off these conferences during these times. I think we're going to end up never going to real conferences again, though, if you guys keep doing such a good job. Okay, so today I'm going to talk about narrative summarization. And what do I mean by that? Well, I have this graphic here. Let's see if I can get my graphics working. There we go. I think this graphic really sums up what I'm been trying to do over the last 7 or 8 years in my research, where you have some time series data. In this graphic, it's a movie. It could be anything. It could be network traffic. It could be, an audio clip, maybe a famous music song, or it could be, speech, text going by in some way. But the idea is that you have some cognitive system. This is our slick-haired guy here. He's watching this stuff go by, and as he's watching the media, or as he's watching the world pass by, he's constructing some interpretation in his head. And in his head, he's building up not only, let's say, a recording maybe of what he's seen, but also an interpretation. And in this graphic really shows my thought that it really needs to be a structured interpretation, in that it has inferences about causality, about implication, about high-level schemas that might be evident in the media. And that such that he can turn around when the experience is over, or halfway through if he wanted, and give a narrative of what happened. And I don't mean a blow-by-blow description of the experience or as it was perceived in the world, but rather this person's interpretation of what they saw. Okay, so it's an additive process and not a transformation of the input to the output. And so this is a problem I've been working on for a long time. And actually, here's my next graphic here. I started this work as basic research funded by Paul Bellow. Thank you very much, Paul. And ONR funded work that I did very early, not very early, quite recently, on 2 ONR projects, working with the Heider Simmel film. I won't show it. I've showed it so many times, but the film is about triangles and circles moving around a box, and similar to like this one here. And as a basic research project, what I really wanted to do is figure out how do I take that film as input and turn it into a text narrative as output. And so when I say basic research, in the United States, we call this a 6-1 research. It's a designation in the congressional budget, 6-1, meaning kind of stuff that's cool, that maybe people can come up with some story about how it might be relevant to the government or to our interests as a science community. But it's basic research. It's kind of hard to get that money, especially, as Paul knows, it's very competitive to get basic research money for kind of off-the-wall projects like triangles moving around a box. But now, since then, since 2019, I've transitioned to what's called applied research, which in the United States, again, is what's called 6-2 research. It's quite easier. It was quite a lot easier to get than 6-1 research. You're not competing against the best minds at the best universities all across the country for 6-1 research. But instead, you have to actually make it a little bit more practical to the funding agencies in some way. And in this case, I started doing work applying exactly the same technologies to a military domain around what's called the synthetic training environment. Synthetic training environment is one of the US Army's new pillars, meant to replace all of the simulation environments that they've had been working on over the last 20, 30 years with a single simulation environment that's meant to take care of live, virtual, and constructive simulation for training and other purposes within the Army. And so the idea of that, given that there's billions of dollars available now for doing research in this space, I said, okay, I can do this. I'll just take the triangle research and I'll just apply it directly to the synthetic training environment. Okay, so that is to say, you'll have human soldiers controlling avatars in some virtual world, and they'll be fighting virtual battles and things like that. And I'll just apply the same technology and build narratives of what happened. And the Army, they'd be super happy to have such a thing, because in the military, after a virtual exercise or a real exercise, we'll do what's called an after-action review. And part of an after-action review, at least the first part, is what happened. And it would be nice to be able to automate that, specifically, or especially because people who are in those virtual environments don't get a full view of what happens. So we needed to hook this into what the Army is calling the synthetic training environment. But of course, it doesn't exist yet. That's a kind of a problem for doing research in this area, is that it's a well-funded space for something that doesn't yet exist. Our own institute tried to address this gap by building what's called a rapid integration and development environment, we call it RIDE. It's a game-based simulation environment. When I mean game, it's based on the Unity game engine. Mainly, so it's just Unity as a game engine with a really large buffer of programmer interfaces to allow you to integrate lots of different technologies. So it allows for the importation of real terrain captured from drones flying over the desert and things like that. It has a nice agent and group AI system for both neural network-based behavior modeling and traditional kind of finite state machine and behavior trees. So lots of machine learning integration, has network multiplayer, so you can run hundreds of people in networked environments, cloud service integration, synthetic data generation, I use that a lot. So the question is, could we add narrative summarization to this thing? So what would that mean? So this is like a screenshot of some multiplayer. I think I play a video here. Yeah, a video here. We have a 9-man squad moving around a virtual version of a fictional city that really exists in Fort Irwin, California, in the Mojave Desert or in the high desert. And here you have 9 of us doing some sort of squad formation around this virtual village. I think I'm in here somewhere. Yeah, there I am. What we were doing on that day. So the idea is this: can we take this kind of thing and with battles against other humans, battles against other AI groups or whatnot, and generate narratives in exactly the same way we did it in the Heider-Simmel film. These days, people are actually trying to do this in an end-to-end neural network system. Okay, going from video of especially things like basketball games and football, soccer games, and translate them directly into text by employing enormously large amounts of data. And I think actually one day that might actually be possible. I haven't been a huge neural network fan my whole career, but I'm amazed by the stuff that people are doing. And I do see some prospects for this on the horizon to be able to do this kind of stuff. It's not going to work great yet in our domain because of the lack of data. And it actually doesn't work great in any domain, even when there is lots of data. There's lots of things that have to be solved. And I think today in my talk, what I want to do is kind of highlight the unsolved problems, the really challenging things that are going to make it really, really difficult to build an end-to-end neural network model that transforms videos or simulation environment experiences directly into text narratives. I mean, of course, there's the lack of data, but what else is there? What's the real problem that's going to make this too hard to do? And I'm going to, in the approach that I'm going to talk about, we're going to have an intermediate representation. It's going to be something between the soldiers moving around a virtual environment and the textual representation at the end. And so we're going to do something in the middle here. It's going to be some sort of graphical symbolic representation. And I don't know what we'll call this just yet. Maybe in the next slide we'll have a name for it. But it's going to be an intermediary. It's going to be something that represents the situation, the interpretation of what happened through some combination of perception and interpretation. And once we get it into this kind of graphical representation, symbolic graphical representation, then we'll do this translation step to go from this structured thing to a linear text. That sounds like fun. Let's do it. Well, I don't know what we'll call it. I tend to call them proof graphs because of the way they are constructed, which I'll talk about later. But you can imagine that, after watching one of these long, hour-long military endeavors, you're going to end up with some structured representation. It's going to have at the bottom here a bunch of things that, like observable things that happened, and on the top parts, it's going to be more of the interpretation stuff that isn't evident or viewable. It's the kind of in the narrative world they call the extra diegetic layer. That is the layer that describes the thing that you added to what you saw in order to make sense of it. It's the sense-making aspect of it. So here in the bottom, we'll get some definitions here. That when we're looking at pixels on the screen or traffic in a network simulation, the thing that you're going to need to get out of that to start with is some observations, like some observations about the city that we're walking around, about where the group is moving and what kind of formation or other behavior they're doing, how they're interacting with other groups, enemies in the environment, that sort of thing. And the stuff you're going to try to do is figure out what assumptions do I have to make in order to make sense of what I'm seeing. And so in this graph here, the assumptions are actually going to be these oval things. And it's a structured graph such that the assumptions explain for you different entailments. These are also things that you can't immediately see in the space, but rather things that you infer that help you make sense of what's going on. So our assumptions allow us to infer things like this. Maybe this is a disaster area, and maybe this group is on some search and rescue mission, and that explains why they're maneuvering in this squad traveling formation. And it's only in the combination of all of the things that you see, especially in a long series of events, that you're able to find some set of assumptions that bring coherence to the situation. So this is kind of an intermediate goal. We're going to get to this point halfway through the process, where we have a very large structured representation that it helps explain the observations that are evident in the data. So how do we get those observations? Here's how I did it within the triangle world. I didn't hire anyone. I enlisted tens of thousands of kids, mostly, to show me what low-level actions look like in the world of triangles. Okay, so I built a game called Triangle Charades and Hydersimul Interactive Theater, and I really did get tens of thousands of people to make animations of triangles moving around screens, mostly in a touchpad environment like the these iPad devices, sometimes in a desktop environment. And we collected really tens of thousands of animations and annotations on those animations to give us, to be able to do that very first step, to go from the observations in the world, in this case, triangles moving around the screen, to that linear set of symbolic actions, things like, the big triangle pushes the little triangle, things like that. It was a great time, a lot of fun. And I thought, okay, well, why don't I do that again? I'll hire 10,000 teenagers to run battles in military simulations and doctrinal formations. And that wasn't going to work. So I had to come up with some other solution. And I don't know, aside from the fact that it's very difficult, in the Hydersimul world, you have multiple characters. There's a triangle, a circle, a door, another triangle, but it's really only one person. So it's actually much easier to coordinate the collection of the data. I mean, a single person can make a movie. And so there's not the coordinated effort you need in the military case where you had to get a squad of 9 people together to do actual behaviors. So the real prospect of collecting tens of thousands of annotated training examples of behaviors in the military case seemed like an impossibility. Particularly since this thing really didn't exist yet. So the trick that I used in this current environment is one that we're seeing a lot more in the neural network perception field, especially in things like self-driving cars and whatnot, which is to generate synthetic training data, that is to get AIs to, or vision and graphics algorithms to generate inputs for you that look enough like the real world that you can train an algorithm to recognize the same behaviors or images or whatever in when it's humans doing it rather than the AI. Here's a picture I'll show you. Here's a graphic where, I don't know, we have a synthetic squad. I don't know where they're doing some sort of crazy maneuvers. I think this is running at 3 or 4 times real-time speed in the simulation environment. So they really do like little ants running around the environment. It's a lot of fun to watch this. And you can parameterize this, how far away you want them to be or what sets of formations or behaviors you want them to cycle through. And basically you're just generating data. It's just time series data that actually doesn't look too much like what a human group of people would do in the simulated environment. It allows you to at least start building a model that says, how do I detect that time series set of events that are going on in the behaviors of people in the environment? It really, it actually doesn't look much like people. But here's another one. This is a slightly more complicated more time series based behavior of what's called bounding overwatch. Is when you have 2 fire teams in a squad and they're each sort of guarding and shooting at the enemy so that the two fire teams can independently or can advance across some terrain. This is in a fictional town, and again, a siege out in the desert. And again, it doesn't look at all really like how people would do it in the real world, but it sort of captures some of the character of how it would be done if it was run by human teams. So how well does it work? Well, we have to go, again, collect a bunch of data of humans running around a virtual environment in a network multiplayer mode, and then use that to train the system. And if you do that, it doesn't work. You get really bad performance on the authentic human test data. But if you really work hard and you do things like domain adaptation, where you're adding a lot of noise and fuzz and timing issues and rotational data and separation adaptations, and you do different kind of tricks in your neural network models, you can get a really good performance on that series of events that are happening here. This kind of the different formations that groups might be doing, the different engagements, the attacks that they might be doing against each other. So you get good performance on recognition, that sort of perceptual stuff, with no authentic training data, just authentic test data in order to tell how well you're doing. So that's fun, I guess. I've been playing a lot of video games this summer. But now we got to solve this next problem. How do we build that graph from that linear set of observations that we're getting from the perception system? And as many of you know, my longtime collaborator has been Jerry Hobbs here at University of Southern California, now an emeritus professor here. And Jerry Hobbs was, I think, solved this problem, but not in the military domain or even the Hyder-Simmel triangle domain, but rather he was most known for his work in computational linguistics. And he borrowed an idea from one of America's greatest philosophers, Charles Peirce, from the 1800s. Charles Peirce had this idea that if you had a set of axioms and you could do, and a set of observations, you could do something that's kind of reminiscent of deduction or induction that you would see in other kinds of reasoning systems. But the word he used was abduction. So given a set of axioms, what set of assumptions would logically entail the observations? Let's just say, if you had some things that you see in the world, like soldiers moving around a battlefield, and a set of axioms about soldiers moving around battlefields, what set of assumptions could you make that would logically entail these observations? And this is what we're going to use to build this graph. So Jerry did the same thing 100 years later, not more than that, I guess. Except he was working with text, and so the words are the observations here. So his idea was, given a knowledge base, what meaning would logically entail the words in a discourse? And I think this really captured, the effects of this idea, I think, haven't really been fully understood yet, but it's a clever idea. It's the idea that when we think about language understanding or sense making in general, what we're doing is trying to come up with assumptions about the meaning. Okay, assumptions about the meaning that explain the words as they're passing by, or the images that we see in a video, or the movements in the squads in a virtual environment. So Jerry's, he not only had this idea, but a really nice implementation called weighted abduction. And the idea was as follows, that we would encode our knowledge base as a set of first order definite clauses, kind of a slightly restricted form of first order logic. But we're not going to do theorem proving or anything like that. Instead, we're going to do backchaining from the observation. So we see some observation in the world, we have many rules maybe about what might lead to that observation. And we'll just backchain and see and make some assumptions about what would explain the observation. And then if you do that, and you have tons of observations, then you have this messy set of possible assumptions. To make some coherence out of it, you're going to do unification. You're going to try to take some of those high-level assumptions you made about the observations and you're going to try to unify them, to coalesce them, so that you have a more cohesive, or what's the word? I think there's a fancy word for this. A more, well, a better explanation. Okay, so unification here is about reducing the cost of the assumptions that you're going to make that explains the world. So this is called interpretation as abduction. I thought it was a brilliant idea, and we early in my career, or my collaboration with him, I did a lot of work with weighted abduction and whatnot, and people didn't like it for a lot of reasons, mainly because it had arbitrary weights. I'd actually, these days, where we're putting arbitrary weights on neurons in our networks, I don't know if people would have the same reaction to it, or same adversarial stance toward weighted abduction as they did back then. But people didn't like this idea of sort of arbitrary weights on, because they didn't seem to have a interpretation that people could the weights didn't seem to have a semantics that people understood. So I haven't done many technical advances in my career that I'm really super proud of, but one of them is this. It's this idea of Etcetera abduction, and actually it was just a twist on another one of Jerry Hobbs' ideas. It was Jerry had this idea of what's called he called it the Etcetera literal, and basically it is another assumption that you make in your definite clause. A definite clause is a set of literals that are that in abduction are the assumptions that entail the consequent, which is the observation often or sometimes. And so Jerry's idea was to because definite clauses in first order logic need to be true 100% of the time, he needed some way to make definite clauses defeasible. And rather than change logic or use some fancy modal logic or something like that, he just had another brilliant idea. He said, we'll just throw in another literal called the Etcetera literal that is all the other things in the universe that have to be true in order for the other antecedents to logically entail the consequent, called it the Etcetera literal. And my contribution to this narrative was to identify that the probability of the Etcetera literal is equivalent to the conditional probability of the rest of the antecedent given the other antecedents in the first order definite clause. And so what we can do then is we can judge the quality of any solution in this space as the joint probability of these Etcetera literals. Either if everything backchains back to some sort of Etcetera literal, then we can naively compute the probability of the solution of the set of assumptions as the product of those probabilities. And I say naively because it's exactly equivalent to naive Bayes. It says that you're assuming conditional independence of the things you don't know about, all those rest of the things in the universe that have to be true. One of the things that falls out of this is that the most probable explanation of any single observation, like the troops in a particular place, if you look at that in isolation, then the most probable explanation is always its prior. It's always the null explanation that, I don't know if these things happen. And it's only in looking at things, the possible explanations for many things, that we have some opportunity to unify some of those assumptions. And here you're unifying the Etcetera literals. And by doing that unification, you can drop a factor, because now if you had two things that had probability mass, you're going to combine them. Now you have one thing that has probability mass. You've just dropped a factor in your calculation. Your probability can increase. And so if you can do enough of that unification in the right places, then the probability of a graphical solution can beat the prior probabilities of the observation. So I think this stuff is really cool from a technical perspective. And if you want to go on GitHub, and there's some nice tutorials I wrote about the idea of Etcetera abduction, and there's software packages in different languages and stuff like that. So here's what one of these literals look like. We have a unique predicate for every axiom, okay? There is some conditional probability of the consequent given the rest of the antecedent. And you have all of the variables in the axiom, all of them, including the ones that only appear in, that had previously only appeared in the consequent, meaning that all of these variables are universally quantified variables. That turns out to be super important. So you have all, so what this is saying is that there is some bag of conditions of the universe that is this probable, that relates all of these things in a particular way that allows the rest of the antecedent in this definite clause to entail consequent, etc. But it's just a concept. We have to get it to work. So the problem with abduction in general, or logical abduction, is this problem of combinatorial search. And it's a really nasty search problem in the first order case. I have this graphic, it's kind of fun. Again, it's too small to read, but I'll let that spin away here. This is like a search through all of these possible explanations for all of the individual literals, where we're trying to unify them as much as possible. So we're searching through every possible way to unify the assumptions in every possible combination of every possible explanation for every observation. It's a lot of everys, and that's where the combinatorial nastiness of this problem comes from. And what that means is you can't have a really deep search. You can't search 10 layers deep or a very broad search. You can't search 1,000 observations to find this best one, because it's a nasty search problem. In fact, if the best approach so far that people have been able to come up with has been to use linear programming as and the solvers like Garobi and things like that as the way to find the optimal solution given some depth of backchaining in your knowledge base. So yeah, in particular, Noya Inoue from Japan, the Tohoku University, is a really nice weighted mexat solution to this problem that's probably the best, certainly the best available currently for optimal solutions. But even there, it's an unscalable, it's an unpractical solution because, well, look, even in the Hyder Simmel case, we had, I don't know, something like 120 observations, things like triangles attacking each other and things like that. Way too big, way too big. And even with a knowledge base that you might have to go back only 6 or 7 back chaining layers deep to get the real essential meaning. It's just a totally implausible to apply a weighted mexat algorithm to that and get the optimal solution. So the only scalable approach to abduction is to do incremental search, to do a little bit at a time. And this kind of goes along with our intuition that, you don't wait to the end of a movie in order to interpret what happened. Because otherwise people wouldn't laugh or cry or scream in the middle of a movie. They're doing in real time, they're watching it, they're coming up with their interpretation of what's going on and they're having their reactions because of it. So that's how it has to be done in our world as well. Back to that original graphic, you're incrementally building up your interpretation. And what that means is that you might get it wrong, especially in the beginning. You might, you don't have enough information. So if you commit too soon to what you think is going on, you can be stuck with that commitment for a long time. Actually, someday someone smarter than me will figure out how to back up and fix misinterpretations that you made early on in the movie. But I don't actually have a whole lot of, I don't think people do that very often. In movies, directors have to explicitly show you what you got wrong. What was that? The Usual Suspects is always, I love that movie. Always is a good example. It's like at the end of the movie, the director has to literally show you all of the misinterpretations that you made at the very beginning of the movie or throughout the movie in order for you to understand what goes on. So I think that's probably more likely the approach. Yeah. Combinatorial search. Okay, so combinatorial search is going to allow us to unify assumptions and find solutions to an interpretation problem that beat the prior probabilities. And in the end, they're all going to look like this. The best solutions are always going to have this kind of shape to them. They're going to be observations on the bottom, some intermediate entailments, and then a handful of high-level assumptions on the top. Okay, that's how, at least in probabilistic abduction, all the solutions are going to look like this. So then what? So actually, I wanted to actually show you both backward and forward chaining rules. Let's start with the backward chaining rules. If you, let's see here, here's an observation. Yeah, a group enter here. If you see that a group is entering some area, then that's the consequent, right? That's kind of the group is entering. So we're going to back chain from this. If we can unify this literal here, group enter, with some observation that we made, then we might make these two assumptions. We could assume that, hey, this might be the area of operations of that particular group. And we'll make this other assumption, which is the etc. literal. It's like all the other things that have to be true of these entities in the universe, which happens at this probability, that will make it so it's always the case that if this is your area of operations, then you're going to enter the area. Okay, that's what the etc. literal provides for you. Okay, so that's a backward chaining rule. We're going to use that in order to come up with some assumptions about why someone might enter, why some group might enter an area. Here's a kind of a mid-level abstraction. If we're assuming that the civilians have fled the area, then it might be reasonable to assume that it's a disaster area of some sort. Maybe it's a chemical dump of something, who knows? But it's a disaster area. And this other conditional probability reified as an etc. literal that says the conditional probability of, that the civilians have fled given that there's a disaster area is some value here. And these numbers I just make up because I'm making up a lot of things. So those are back chaining rules. But what's kind of neat about this is that, at least I used to spend a lot of time trying to think about how to turn these kind of literals into text. And finally I gave up and I just started writing the templates as definite clauses, actually simple definite clauses. So here's a forward chaining rule that generates text. It says, if you're assuming the conditional probability of this given that for these entities, then the text that you could output, you could have many of these, the text you could output is that the disaster area in, that's a string constant, area is a variable, and then another string constant prompted its inhabitants to flee, another string constant. And then when you forward chain off of your assumptions, because this variable is bound to something, then it gets swapped in here. And then you end up with these kind of long strings of text that perfectly adequately just serve as a template for what it is you're trying to say in a literal. You can have multiple ones. Here's one. So if you're assuming this conditional probability here, then the text might be, whatever this group is, they arrive at its area of operations in whatever area it was that's bound to it. And you can get fancy, and in my system, I do get fancy a little bit. You can have dependent possessive pronouns for the group, so that the group entered the area to perform its mission. Okay, you can use this kind of stuff in order to swap it out for the names of places, groups, proper names, common names, whatever you want to do. And that turns out to be trivially easy to do. So if you already have the relational structure, then language generation turns out to be super easy with simple templates. Comes out pretty stilted, but we can fix that in just a second. But we do need to select which of these literals we're actually, or assumptions, which ones are we going to choose to put in our story, in our textual narrative. And there's lots of ways to do it. There's been really a lot of really great work. Trabasso, I really like David Elson's work on story intention graphs. Who else? Mark Finlayson, who we'll hear from later in the conference, did great work as well on props stories using these kind of intention graphs to generate text. But there's lots of really good work in here. I use in my works, I started with a very simple thing, which is what I'm calling the shallow causes heuristic. I'll just pick the lowest level conditional probabilities, the thing that link the immediate assumptions to the available observations. And those can get generated in things like this. So that you have this low-level assumption that links this to this can be articulated as the population of Rasish had fled, leaving the area completely abandoned. Okay, you're sort of ignoring this high-level assumption you made in the narrative that this is a disaster area. But actually, that like combined bits that you get from all these low-level things kind of imply that. And I think this is really what's going on, certainly in movies, but definitely also, as well in textual narratives, is you don't have to beat people over the head necessarily about the high-level things. If you give them enough clues about the right interpretation or the intended interpretation at the lowest level. And so this is actually, I think, ripe for kind of evaluations, kind of more empirical evaluations, different strategies and narratives. Also cross-cultural studies about, actually I've done some of those cross-cultural studies where we find Chinese narrators tend to add more of the top level stuff, whereas American narrators stick mostly to the diegetic level. Interesting stuff. Anyway, I think that's kind of, oh, what's this? This is, okay, I took a day off of military stuff and I went back to the old triangles. I can't get away from these triangles. I love them so much. But the hydrosymbol film, I had got to the point where I could generate a full interpretation of the hydrosymbol film, the logical interpretations. And we had a very complicated system for turning that into text, but I said, okay, let me just spend an hour. I said, I'll author templates for all of the literals in the hydrosymbol knowledge base. And it was pretty good. There's some problems in this interpretation, which isn't the optimal one. But, it kind of sounds like, it's very much like the text that Hyder himself wrote about the hydrosymbol film back in the 40s. The circle shook in fear. A little triangle partly opened the door out of concern. The circle exited, making her escape. The big triangle hit at the jammed door, pushed the door, trying to get it unjammed. I like that stuff a lot. It's more than just the events that happen. It sort of captures the fear and glory of the escape. Filled with joy, the little triangle danced around. I can't see because I'm blocking my own view here. Big triangle went outside to investigate. Little triangle escaped out of the scene. I don't know, it's very nice. It was rewarding to get to this point. It's still pretty stilted, actually, and I wonder if we could do better. So the next thing, to make this stuff better, we need to be more modern in our approach. And the thing we're gonna do is a very modern thing, which is to rank the kind of possible solutions of generation using tuned language models. So here's a GPT-2. It's our favorite, well, until GPT-3 came out recently. We used to use GPT-2 a lot. And what we did is we fine-tune GPT-2 with all of the Wikipedia pages that describe 21st century battles. Okay, because we're making, after-action reviews of battles. So, it's very sad, but there's actually been a ton of battles in the 21st century. Not all of them involving the United States, thankfully, but there's been, battles after battles over the last 20 years. And people care a lot about those battles, so they write large, long narrative descriptions of them. And so we just gathered up all of those narratives and then took GPT-2, the off-the-shelf version, and then fine-tuned it. And you can use it as a generator, which is kind of fun. It sort of creates stories of battles that never happened. And they seem, pretty realistic. Here's one about some battle. This battle never happened in Damascus. But more importantly, you can use it as a ranker. So in the language model world, if you want to say how well is this text predicted by the model, which is a notion of perplexity, you can feed it into GPT-2 and add up to get the perplexity. So here's a not very good version that gets a decent perplexity. And because, we're not going to get a great language model of military stuff with the amount of data that we use, we're just using ranking. Okay, we want to lower the perplexity of any of the variations that we might come up with. in order to pick which is the best version of the generated story. And we could do that for the Hyder Simmel film. I don't know, I didn't try that to come up with the best version of Hyder Simmel as a 21st century battle. It's kind of sad, but it is kind of a battle in some way. Maybe I should do that for fun. But this is exactly what we're using for after action review narratives, is using a GPT-2 trained, fine-tuned model to do ranking of stories. And so in the, if you look at this, we kind of bookended this whole process with two neural network approaches. On the front end, we have this combination of kind of ResNet tuned convolutional networks with kind of recurrent networks on top to get that kind of event stream out of what's in the observations, trained on synthetic training data. And on the back end, we're doing a kind of ranking thing. And so the question is, can't we just make this an end-to-end model in some way? You want to go straight from these, maybe from the pixels, who knows, I don't know, probably that's too much, or maybe an overhead view or something like that. And have an end-to-end neural model that just spits out this thing, okay? That would be, is it on the horizon? Some people really think this is like next year, but it's not gonna happen next year. But it could be soon, but what's the problems that have to be overcome to make this a reality? So on the pattern recognition, if we think about, kind of like dice up our process and we think about what needs to be neuralized in this effort, then we have to do a bunch of stuff. So on the pattern recognition side, we have to figure out the data scarcity problem. And maybe the synthetic training data is an approach, but it means that you're going to have to piecemeal these problems and stitch them together one by one rather than do a full end-to-end training. So, but we can train individual pieces maybe and then stitch them together. And on the back end, ranking, that's easy. I did that myself, which is impressive for me, not knowing anything about that stuff. But you could probably also go straight from the graph to the text, stylized text, if you have enough data. But really to pull that off successfully, we're gonna need to make some advancements in what's called graph embeddings, or the latent representations of those structured networks. And there's enormous progress in that space going on all the time right now in the neural network embeddings of graphical representations. I guess what really needs is a stronger push toward the embeddings for first order graph representations. What I mean by that is each of those nodes in the graph is a first order literal, that is a relationship between one or more entities in the literal, and each of those entities might appear elsewhere in the graph. So that's, but someday someone will figure that out, somebody smart. Here's the hard part though. The interpretation as abduction requires that we have a first order knowledge base. Actually huge progress going on there. There's continued progress on trying to extract, mostly from text, these kind of common sense or even specialized knowledge rules that might allow for that kind of defeasible inference between latent representations. I'm kind of hopeful about that. A little bit harder is to do this inference with variables. We need to, once we assign a variable one place, we need to swap it out somewhere else. So your whatever latent first order inference has to be done, it has to be able to carry across variables, both in the antecedents and the consequences, and maybe elsewhere in your solution. And the elsewhere in the solution part is about unification. Unification, it's a core, it's been the bread and butter of logical AI for its entire history. And it's something that is still extremely difficult to imagine how it could be done in neural networks. And maybe it could be trained, I don't know, but it's totally necessary. It has to be fast and it has to be really good, okay? And you might imagine trying to build systems that unify two English sentences, okay, to make them the same sentence by taking bits of either one of them and jamming them together in a coherent way. It has to be nearly perfect in its ability to do the unification. But I feel like there's some hope for doing this unification in latent representations. The harder part for me to imagine in traditional architectures is pulling off combinatorial search. Now, I'm convinced that you cannot do this kind of translation of this to this without combinatorial search. Okay? You have to be able to consider all the possible explanations in order to find a good one. And it's going to require unification and inference and these latent knowledge bases and whatnot. But there's nothing in my mind that prevents us from imagining doing combinatorial search in the architectures of feed-forward neural networks. It won't be all feed-forward. It'll be feed-forward with search, okay, or parallelism, or something that, some other level of labor that is more than just cross-product of latent representations. Some sort of architecture that does runtime search. I'm really, in my work on human brains, when humans do a lot of interpretation of stories, it isn't an instant thing, right? You don't get input to output. So your brain does a ton of work when it's trying to make sense of a story. It's burning a lot of oxygen in the bold response. At certain key kind of, we call them convergence zones in the brain, these kind of like default mode network and whatnot. A ton of work is going on there, burning a lot of oxygen. What the heck is it doing? And in my mind, what it's doing is combinatorial search, unification over all of the knowledge that's stored in those cortical areas that are trying to come together in order to find some interpretation of all those things that the cortices are recognizing that makes sense. So I'm actually bullish on the idea of neural narrative understanding and generation, but we have a long way to go. Okay, I'm gonna end it there. How'd I do on time? Hey, not bad. So I think what's gonna happen here next is that we are going to close down this session, and I'm going to move.
Paul's going to ask you questions. Paul's asking you questions.
Okay, let's do that.
8 minutes.
I'm not asking. I can ask one question, but I thought we were supposed to get questions along the way. We didn't actually get any questions.
Oh no, there's a lot. They're all in the invited talk Gordon Slack channel.
I'm on that channel now, and I don't see any questions. Oh, there's load new messages. Ah, okay, good. I don't have to ask you a question after all.
Oh, good.
Should I just pick one at random, or?
Yes, go ahead and
Sure.
select select a few of these questions.
Okay. So here's a biggie. One from Shivali. Are there principled ways to think about weights and abduction? Why were people complaining about weights?
Well, yeah, again, I think in this neural network era, people complain less than they did back then. I think, you got to remember the time. I was just thinking about this the other day, like if the next AI textbook would have like POM DPs in it, like these kind of probabilistic models that and at the time, if you asked me 15 years ago, I would have said, there's no way that'll never be jettisoned from AI, core AI theory. But now I'm like, if they drop POM DPs from computer science or AI textbook, no one would even notice. So sorry for all you POM DP researchers out there. But that was the era we were living in. Everyone wanted probabilities, right? They wanted some way, and me too. I think I sold this to you, Paul, that we had to do this in probabilistic way because of integration, right? It only made sense to integrate with, probabilistic parsers or probabilistic perception engines and things like that. If we were all in the same field of probability, and I think there's still some merit to that idea, especially in integrative systems where you have to train them independently or architect them independently and then jam them together. Honestly, maybe that's less important these days because of end-to-end. Well, to some people, it's probably going to be less important. So who was the person? It was Katya Ovechkinova, had a nice paper maybe about 6 years ago or so. She's a Russian scientist who is now in Germany, I believe. She showed that there was no way to get a probabilistic interpretation of the weights in the axioms of weighted abduction. Okay, so it's a nice proof in that paper. Ovechkinova, kind of a tough word. I'll put it in the chat so you guys can find it. And that kind of said, okay, well, we need to find something else then, a different approach. Why not? And honestly, you know, my approach to probability, especially with its naivete and the naive Bayes sense, people don't like that either. And there's other folks who take radically different approaches to probability in logical systems that I think is nuts. But so it's not the only way out there. But this, you know, it's fine. In the end, because these are unobservable states, okay, that's the thing. These assumptions that you make are unobservable. You're never going to get good probabilities on what they actually are. And even in the case, you know, think about the semantics of what they mean. They mean all of the rest of the things in the universe that have to be true in order for the antecedent to logically entail the consequent. Okay, it requires, you know, knowledge of the universe that's way beyond our comprehension or ability to measure as a probability. And so the only thing you can do is tune them, okay, with test data, exactly the same way you would do with a neural network model and backpropagation. Okay, there's some additional constraints because of probability theory that you can possibly take advantage of, but in the end, it's just a weight. Sorry, everyone.
Okay. Take another one. Do we have time for another one, Matt? Yes.
Yep.
Okay. So Ken Forbest asks about the lack of backchaining in the system being a bit surprising, and asking if you use beam search instead.
Say that one again. The lack of what in the end?
Backchaining?
Backchaining, the lack of backchaining.
My understanding was that it was all backchaining. Is that right?
Well, okay, so it is all backchaining. You backchain from the observations given your axiom, your definite clauses, and your knowledge base.
He chimed in to correct that he wanted backtracking is what he meant.
Oh, backtracking.
Oh, backtracking. Okay, yeah. So you can imagine, well, backtracking could mean several different things in different places here as well. But maybe I'll assume he means backtracking with respect to the interpretation that you get. And there, I do feel like that is uncharted territory that somebody smart should tackle. But it's tricky, especially when you're already pretty resource constrained. I mean, the nice thing about the incremental abductive framework is you can do this with almost any resources you have available and still be real time. You're just going to suffer in your depth of backchaining and your beam of how many solutions you're going to keep around as you're watching the movie, and the window of things you're going to consider all at one time. And any one of these variables will prevent you from getting the cool interpretations that you wish you could get. So you probably have to tune those parameters with some test data in order to get it to be working the way an interpretation system should work. But I don't know, that probably didn't answer a backtracking question. So maybe, Ken, I'd love to talk to you more about it and answer your question. In the Slack channel, which is, I guess, where we're all going to head now. And for myself, I think it's room 4 on the, no, it's not a Slack channel. It's a.
Both of those things will be true. So the Slack channel will stay open for the remainder of the conference. You'll be able to interact with people through there. And we are going to start the poster session now. And I will now